In this video, we're going to be talking about nonlinear inequalities. Let's talk about polynomial inequalities first, ones that are not linear. Did you know that it used to be illegal to pump your own gasoline in the state of Oregon? A ban of self-service gas stations was in place in Oregon between 1951 and 2023. Example 1 says, let's say that you are taking a road trip through Oregon and you decide to stop at a gas station to fill up your car with gasoline. You have a $20 bill in your pocket. You see that gasoline is $4 per gallon, and you decide that you want to give the gas attendant a $7 tip. How much gasoline can you get? So let's first come up with an expression to represent our total cost. Our total cost is going to equal the cost per gallon times the number of gallons you purchase and then we have to account for the tip, so we're going to add on the tip. Now, I'm going to throw in some variables to represent this total cost. So I'm going to say let y equal the total cost. Our cost per gallon is 4, and then because I don't know how many gallons of gas I'm going to purchase, I'm going to call that x. And we do know that the tip is going to be $7. So we have this expression 4x plus 7, which represents our total cost. Now, because I'm limited to having a $20 bill in my pocket, I need my total cost here to be less than or equal to 20. Now, there's a few different ways I can go about solving for my solution, and one of them is algebraically. Let's go ahead and take this inequality that we have here, which happens to be a linear inequality, and isolate our variable x. I'm going to start by subtracting 7 on both sides. And we get 4x is less than or equal to 13. Now, dividing by 4 on both sides, we end up getting that x is less than or equal to 13 divided by 4, which we can represent as the decimal 3.25. And remember from earlier, x represents the number of gallons of gasoline that we're purchasing. And another thing about that is we can't really purchase a negative amount of gallons. So I'm also going to say that x is greater than or equal to 0 and less than or equal to 3.25. So to recap, we are solving the linear inequality 4x plus 7 is less than or equal to 20. When we solved that linear inequality, we got that x was greater than or equal to 0 and less than or equal to 3.25. So this represents all the possibilities for the amount of gallons of gas that we can purchase when we stop at this gas station. What's another way we could go about solving this linear inequality? Well, we have a grid here, and I've gone ahead and I've labeled my y-axis as my total cost in dollars, and the x-axis here is the number of gallons of gas. I've gone ahead and I've also labeled my y-axis so that every tick mark represents $2, and then on my x-axis, I've labeled it so that every tick mark represents 0.25 or a quarter gallon of gas. And that also means that every 4 tick marks gives me a single gallon of gas. Now previously, we've learned how to graph linear equations. And so what I want to do is I want to graph the linear equation y equals 4x plus 7. Our y-intercept for this line is the point 0, 7, which would be right here. And then we have a slope of 4, meaning we would go up 4 units and right 1 unit. So here we have 8, 9, 10, 11. That's up 4 units, and then we would go right 1 unit. And I can continue that pattern and connect these ordered pairs with a line. So I've gone ahead and I've graphed the linear equation y equals 4x plus 7. And now in blue, because we have this inequality here, I'm going to go ahead and graph the line y equals 20. And that is a constant, and so it's just going to be a horizontal line, and it's going to go across this way. And notice that the place where these two lines intersect, if I bring this down over to the x-axis, this value here is 3.25, where we expected it to be because we found that our upper limit for the number of gallons of gas we could purchase was 3.25. Now, if you notice on the graph, let's go back and emphasize this. We are trying to find when 4x plus 7 is less than or equal to 20. In other words, I'm trying to find the x values where my line, my black line here, falls underneath my horizontal blue line because the horizontal blue line represents 20. And so the x values where my graph falls below the horizontal line 20 is between 0 all the way up to 3.25. And so again, that's why our solution set for this example is the interval from 0 to 3.25, inclusive of our endpoints. So again, in other words, we can purchase anywhere between 0 and 3.25 gallons of gas, given that we only have a $20 bill. So let's recap. We wanted to solve this inequality, and we did it in two ways. We did it graphically by looking at the graphs and seeing when does my linear function fall below the horizontal line y equals 20, and we also solved it algebraically. So in other words, the above scenario can be solved using a linear inequality. However, the focus of this section is on nonlinear inequalities. Example 2 says, solve the nonlinear inequality x squared minus 36 is greater than or equal to 0. Start off by plugging in some random values for x to see if they are part of the solution set, or the set of input values that make the original statement true. So I have this nonlinear inequality, x squared minus 36 is greater than or equal to 0. And this is an example of a quadratic inequality because the thing that we're looking here is a quadratic and it has a squared term as the highest degree. So I'm going to go ahead and plug in some values. Let's say we want to check if 0 is in our solution set. So anywhere I see an x, I would replace it with 0, and I would simplify this expression. 0 squared is 0, and I would subtract 36. 0 minus 36 is negative 36. And I want to ask myself, is negative 36 greater than or equal to 0? It is not. It's not a true statement, and therefore we can come to the conclusion if our solution set, we're calling it S, so S equals our solution set, then we would say 0 is not an element of our solution set. Let's try a different value. Maybe 2 will work. So I'm going to square 2, and I'm going to subtract 36. 2 squared is 4, minus 36. That would give me negative 32. That's also not positive or 0, so that would lead us to the conclusion that 2 is not in our solution set. Why don't we try 6? So if I did 6 squared, 6 squared is 36, minus 36, that ends up giving me 0. Now 0 is greater than or equal to 0, so therefore I can come to the conclusion that 6 is in my solution set. But I can't keep just testing all the numbers that are out there possible. That would take me forever. So how could we do this in a way that would be more helpful? In the previous example, when we were looking at the linear inequality, it was helpful for us to look at the graph. Let's do something similar again here. So I have a quadratic y equals x squared minus 36. Now, this is a quadratic function that has a vertex at the ordered pair 0, negative 36. So if I were to do a really rough sketch, here's my y-axis, here's my x-axis. X squared normally has its vertex at the origin, but we're subtracting 36, so our vertex is going to be down here at 0, negative 36, and then when we graph the parabola, it's going to face upwards this way because our leading coefficient is positive, and so our parabola is facing upwards. Now, it would probably be helpful for us to figure out our x-intercepts, and there's several different ways that we could go about doing this. Let's look at one of the ways. If I took x squared minus 36 and set this equal to 0, one of the ways that we could go about solving for x is we could factor, and x squared minus 36 is an example of a difference of squares. So it would factor into x minus 6 times x plus 6 is equal to 0. Then from here we could use the zero product principle and set each of my factors equal to 0 and then solve for x. And if we do that, we would get x equals 6 and x equals negative 6. Now, an alternative way we could have solved this equation is because there is no x term, or in other words, the b value is 0, I can use the square root method. What is the square root method? Well, I'm going to add 36 to both sides of my equation, and that's going to give me x squared is equal to 36. From here, I can take the square root of both sides, and then we're going to end up getting x is equal to plus or minus 6, which are the same values that we got using the factoring way. So either way you use it, you get that this is negative 6, 0, and this is 6, 0. So now what we're doing is, again, we're going back to this original inequality, and we're asking ourselves, when is our graph of our parabola greater than or equal to 0? And 0 is the x-axis here. So I want to know, when is my graph of the parabola above the x-axis? For what x values? We saw earlier when we were testing out values, we saw that 0 and 2 is not in our solution set. So we want values other than 0 and 2. And from our graph, hopefully you can see that our parabola is above the x-axis here and here. And so it's going to be everything before negative 6 and then everything after positive 6. So let's go ahead and write that in interval notation. Our solution set is going to be negative infinity to negative 6. And because we're greater than or equal to 0, I'm going to include negative 6. And then we have union, bracket 6, infinity. And here is our solution set for this example. Let's talk about a few definitions. The zero product principle, or the zero product property, says that if you have the product of two or more numbers equal to 0, then one or both numbers have to equal 0. In other words, if a times b is equal to 0, then a equals 0, b equals 0, or they both equal 0. A critical value or a critical number is an input value that makes an expression equal to 0. Example 3 wants us to solve x squared plus 9x plus 14 is less than 0. Now notice again, this is a quadratic because it's in standard form of ax squared plus bx plus c. It's going to be helpful, just like in the last example, if we solve for the critical values or the zeros or the roots of this quadratic polynomial. In other words, I want to solve x squared plus 9x plus 14 is equal to 0. And this is a nicely factorable quadratic, and I'm going to use the x method. So I'm going to place my b value on top, which happens to be 9, and then on the bottom, I'm going to put c. And I'm using it this way because our a value or our leading coefficient's 1. So because that's the case, I'm just going to put the c value on the bottom, which is 14. Now, I want to find two numbers that add to the b value and multiply to the c value. The two numbers that do that for us are going to be 7 and 2, which means that now I can take my equation, I can factor it into x plus 7 times x plus 2 is equal to 0. Now going back to the property that we just learned, using the zero product principle, I can set each of these factors equal to 0. And if I solve for x, I get x equals -7 and x equals -2. Now, why were these helpful to find, these critical values? Well, I know that the graph of a quadratic function is a parabola, and our leading coefficient is 1 because there's a 1 in front of the x squared. So here's my y-axis, here's my x-axis, and I'm going to plot -7 and -2 here. It's an upward-facing parabola, so with a really rough sketch, my graph is going to look something like this. Now, going back here, we are looking for where our quadratic is less than 0. In other words, when is the graph below the x-axis? Because that's where the y values or the output values are negative. So the area where my graph is below the x-axis is happening here, between -7 and -2. So if I'm now coming to write my solution set, is equal to, my endpoints for this interval are going to be -7 and -2. Now we need to decide, are -7 and -2 included in our interval? Well, I know based off this factored form here that if I plugged in -7 or -2 into my quadratic, it's going to make my output value 0. But we want to know when our output values are less than 0. So that means that we are not going to include our endpoints, and on our interval, we want parentheses on our endpoints. So our final answer for example 3 is the open interval from -7 to -2. Example 4 says solve the following nonlinear inequalities. And if you notice, in part A, B, and C, these are all the same quadratic, and we're comparing it to 0. The only difference is the direction of and the type of inequality symbols. And so it turns out that we're actually going to utilize most of the work that we did in the previous example to help us with parts A, B, and C here. So I went ahead and I graphed the parabola that we saw in the previous example. And now I want to know, when is x squared plus 9x plus 14 greater than 0? And another way of saying that is, when is our graph above the x-axis? And our graph is above the x-axis everywhere before -7 and everywhere after -2. So on my x-axis, I'm looking at these x values, everywhere before -7 and everywhere after -2. So I'm just going to abbreviate my solution set to S for part A, and S equals everywhere before -7. And now the question becomes, do we include -7? Well, this ordered pair right here is -7, 0, which means that when I plug in -7 into my quadratic, my output value is 0. And 0 is not greater than 0, so I want to exclude -7. Now I have my union symbol, and I want to include the interval from -2 to infinity, excluding -2. So here's my answer for part A. For part B, notice that we have the same inequality. Now we're just wanting to know, when is the quadratic greater than or equal to 0? So our solution set is going to be almost exactly the same as part A, except now we will include our endpoints. So I'm going to put a bracket on -7, and I'm going to put a bracket on negative 2. And here is our answer for part B. And for part C, notice that this was almost the same inequality as in the previous example, but now we have less than or equal to 0. So coming back up to the previous example, we're going to have the same solution set, except now we will be including our endpoints. So for part C, we have s is equal to -7 to -2 with brackets on each of those. And that concludes example 4. Example 5 wants us to solve the inequality -x² plus 2x plus 8 is greater than or equal to 0. Let's start off by factoring out the negative sign from our quadratic, which would leave us with x² minus 2x minus 8. And we want to find out when that's greater than or equal to 0. And now I'm going to factor the quadratic inside of the parentheses, and that will factor it into x minus 4 times x plus 2 is greater than or equal to 0. At this stage, we want to set our quadratic that we have in factored form and set it equal to 0 so that we can find the x-intercepts. If I divide both sides by -1, on the left side the negative would disappear, and 0 divided by -1 is still 0. Now I can use the zero product principle to set each of my linear factors equal to 0, and we would end up getting x equals 4 and x equals -2. Now, if I wanted to graph this, here's my y-axis, here's my x-axis. I'm going to plot an ordered pair at -2, 0 and 1 at 4, 0, and my graph would end up looking something like this. It's just a rough sketch, and I know that it's going through those ordered pairs since we solve for these zeros here, and I know that it's a downward facing parabola since our leading coefficient, or our a value, is -1. Now we want to know, when is our quadratic greater than or equal to 0? In other words, when is our parabola above the x-axis or touching the x-axis? And that is occurring here, and the x values that's occurring on are everywhere between -2 and +4. So ultimately our solution set, which I'm going to call S, is equal to everything between -2 and +4. And I'm going to include my endpoints and use brackets, because if I plug in -2 or +4 into the original quadratic, the output value would be 0, and 0 is greater than or equal to 0. So here is my solution for example 5. Example 6 wants us to solve the inequality -6x² plus 33x minus 12 is less than 16x. First off, we want one side of the inequality to be 0, so I'm going to subtract 16x from both sides. If we do that, we get -6x² plus 17x minus 12 is less than 0. Because my leading coefficient is negative right now, I'm going to go ahead and factor that out, and we'll get 6x² minus 17x plus 12 is less than 0. Now I want to factor the inside of the parentheses, and I'm going to do this by using the modified x method. I'm going to put my b value here, which is -17, and I'm going to put a times c in the bottom. So a is 6 and c is 12. If I multiply those two together, I get 72. So now I am searching for two numbers that add to the b value and multiply to the c value. And the way that I remember that is I really like the artist Bad Bunny, and in the summertime, air conditioning, or AC, multiplies my happiness. So the two numbers that accomplish this are -8 and -9. Now what I'm going to do is I'm going to make sure to remember my negative sign. Then I'm going to write 6x², and the middle term, -17x, is going to get broken up into -8x and -9x, and then everything else stays the same. And what I'm doing ultimately is this -8 corresponds to this -8, and this -9 corresponds to this -9. The reason that we're breaking them up is so that now we can rely on factoring by grouping. So what I'm going to do is I'm going to group the first two terms together, and then I'm going to put a plus sign and group the second two terms together, because subtracting 9x is the same thing as adding -9x. Now that these are grouped together, in the first set of parentheses, I'm going to factor out the greatest common factor, and that is going to be 2x. And that would leave me with 3x minus 4. And then in the second set of parentheses, the greatest common factor would be -3. And that's going to leave us with 3x minus 4. And a clue that you are doing this correctly when you're doing factoring by grouping is the thing left over in the parentheses matches. So now what I'm going to do is I'm going to pull out 3x minus 4. And what's going to be left over is 2x minus 3. And this is all less than 0. Now I'm going to go ahead and take this quadratic and I'm going to set it equal to 0. And I can divide both sides by -1. Then from here, we can use the zero product principle and set both of our linear factors equal to 0. And if I solve these equations, I will get x equals 4/3 and x equals 3/2. Now I'm going to draw my x and y axis. My leading coefficient is -6, which means I'm going to have a downward facing parabola. And my two x-intercepts are 4/3, 0, and 3/2, 0. And right now I am looking for when is my parabola less than 0, in other words, when is it below the x-axis, and that's happening here and happening here. In other words, on my x-axis, or my number line, that's taking place everywhere before 4/3 and everywhere after 3/2. So when I am coming up with my solution set, S is equal to -∞ to 4/3, and I'm not including my endpoint because 4/3 would make it 0, and I want to know when it's less than 0, and then union 3/2, infinity. So here is my final answer for my solution set in example 6. Example 7 wants us to solve the inequality x cubed minus 3x squared minus 10x is less than or equal to 0. Now, this is the first example that we've seen that involves a cubic polynomial. The other ones have been either linear or quadratic. And we know that it's cubic because the highest exponent is 3 here. So how do we deal with this? Well, something that you may notice is every term in this cubic polynomial has an x in it, meaning that I can factor out an x, and that would leave us with x squared minus 3x minus 10 is less than or equal to 0. Now in the parentheses we have a quadratic remaining, and that is something that we are able to factor, and it would factor into x minus 5 times x plus 2. Now I'm going to go ahead and take this cubic that's in factored form, and I'm going to set it equal to 0. Now I can use the zero product principle and set each of my linear factors in and set them equal to 0. If I solve these, I get x equals 0, x equals 5, and x equals -2. Now, previously, I have assumed that you know what the graph of a quadratic looks like, which is a parabola, but maybe you don't know what the graph of a cubic function looks like. So here's my y-axis, here's my x-axis, and I'm going to go ahead and plot my x-intercepts just like we've done previously. So there those are. And because, let's say we don't know what the graph of this cubic function looks like, what we're going to do is we are going to use what are called test numbers, because essentially what our x-intercepts do is they take our x-axis or our number line and break them into subintervals. So suppose that I break it here, I break it here, and I break it here. That's going to tell us that my first subinterval is everywhere before -2, in other words, from -infinity to -2. Then my next subinterval would be from -2 to 0. My next one would be from 0 to 5. And my last subinterval would be from 5 to infinity. And because of the way polynomials work, if I chose an x value in each of these subintervals and I plug them into the cubic expression that we're looking at, it will tell us whether our output is positive or negative. So I've gone ahead and I've cleaned up the screen a bit, and I've left the original cubic that we've put in factored form. Now I want to go ahead and I want to choose test numbers that fall into each of these 4 subintervals. And for the first subinterval, I'm going to use a test value or test number of x equals -3. In the next one, I'm going to use x equals -1, x equals +1, and x equals +6. Now what is it that I'm doing with these test numbers? I would like to take this value here, x equals -3, and I want to plug it into the cubic function. Now, it does not matter whether I plug it into factored form or in the standard form here. I do think that it's going to be a little bit easier if we plug it into the factored form, though. So let's take -3 and plug it in. I would get -3 times -3 minus 5 times -3 plus 2. So now I'm going to go ahead and simplify this expression. It's going to be -3 times -8 times -1. -3 times -8 is 24, times -1 is -24. That means that in my function graph, it's going to be negative. Everywhere between -infinity and -2, my function graph is going to be negative. And so if I were to be sketching this, it would look something like that there. Let's go ahead and plug in x equals -1 now. I would have -1 times -1 minus 5 times -1 plus 2. Okay. So 6 is a positive number, which means that our graph would be positive, and so it would look something like that. And then we'll come back down since we know that there's an x-intercept there. Now we're going to use our next test number of x equals 1. I'm going to plug that in. And that's going to equal 1 times -4 times +3, which is equal to -12. That means everywhere in the subinterval from 0 to 5, my graph is going to be underneath the x-axis since we got a negative number. And then we're going to curve up back to this x-intercept. And now we want to test our last value, which was 6. If I plug in 6, we'd have 6 times 6 minus 5 times 6 plus 2. These 3 numbers, all 3 of them will be positive, so my final answer would be a positive number. And I don't really care about what the actual numerical value is. I just care that it's a positive number, meaning that my graph will go up above the x-axis at this portion. So going back to the original inequality, we want to know when our cubic is less than or equal to 0, which is another way of saying when is the graph touching or below the x-axis. And that's happening here before -2, and then here between 0 and 5. And so the x values that we're looking at that's happening on is everywhere between -infinity and -2, and then also between 0 and 5. So our final answer for our solution set is going to be -infinity to negative 2, and I'm going to put a bracket on negative 2 since that would make our cubic 0, union bracket 0, 5 bracket. And here is our final answer for example 7. Example 8 wants us to solve 2x squared is greater than or equal to 5 minus 3x. I'm going to go ahead and subtract 5 on both sides and add 3x on both sides. So that's going to leave us with 2x squared plus 3x minus 5 is greater than or equal to 0. I want to factor this, so I'm searching for two numbers that add to 3 because that's our b value. And then a times c would be 2 times negative 5, that's negative 10. And I'm searching for two numbers that multiply to that. And those two numbers are going to be 5 and negative 2. So let's go ahead and break this up. We have 2x squared plus 5x plus negative 2x minus 5 is greater than or equal to 0. I'm going to group the first two terms together and then the next two terms together. In the first set, I can factor out an x. And in the second set of parentheses, I can factor out a negative 1. And remember, a clue that we are doing this correctly is that the things left over inside of the parentheses match, which they do in this case. And so we're going to get 2x plus 5 times x minus 1 is greater than or equal to 0. I'm going to now set my factored form here equal to 0 and find our critical values by using the zero product principle and setting each linear factor equal to 0. If we solve, we're going to end up getting x equals negative 5 halves and x equals positive 1. Now we're back to working with a quadratic, so we know what the graph of a quadratic looks like. And let's go ahead and take a look at this quadratic here, and we want to know when that is greater than or equal to 0. Our leading coefficient's positive, and I have an x-intercept at negative 5 halves comma 0 and 1 comma 0, and it's an upward facing parabola. And I would like to know when is my graph either above or touching the x-axis, and that's happening everywhere before negative 5 halves and everywhere after 1. So my solution set is going to be negative infinity to negative 5 halves, and we would put a bracket on 5 halves, union bracket 1 to infinity. And there's our final answer. Example 9 says use the given graphs below to help solve the following inequalities. Part A wants us to find when x squared minus 5x plus 4 is greater than or equal to 0. Now down here below we have this parabola graphed for us, and we want to know when it's greater than or equal to 0, which is essentially when is our graph above or touching the x-axis. And that is happening everywhere before positive 1 and everywhere after positive 4. So for part A, our solution set is going to equal negative infinity to positive 1, and then we're going to have a bracket since we want to know when it's greater than or equal to 0, and then union bracket 4 to infinity parenthesis. Remember that positive and negative infinity will always have parentheses on them in interval notation. Now we're moving on to part B. We want to know when that same quadratic is less than 0 or below the x-axis, and that is happening between 1 and 4. That's when our graph is below the x-axis. So for part B, our solution set is equal to, that should be a parenthesis because we're not including 0 in our inequality symbol, so parentheses 1 comma 4 parentheses. And there's our answer for part B. In part C, we have x minus 1 squared times x plus 2 is greater than 0. Here we have the graph of that function, and we want to know when is the graph above the x-axis. So that's happening almost everywhere after -2. The reason that I say almost everywhere after -2 is because notice that when I plug in 1 in for x, if we simplify that, 1 minus 1 squared plus 1 plus 2, that's going to end up being 0 squared plus, oops, that plus shouldn't be there. So it's going to be 0 squared times 3, which is just going to end up being 0. And 0 is not greater than 0, meaning that 1 is not in our solution set. So how do we write our solution set for part C? Our solution set is equal to parentheses -2, comma 1, union 1 to infinity. So that's how we would denote the set of numbers that are greater than -2, excluding +1. So there is our answer for part C. Now, for part D, I want to know where is my graph below the x-axis or touching the x-axis. So it's below the x-axis everywhere before -2, and then I have to account for this one location at x equals +1 where it's also touching the x-axis. So how do we denote a set like that? Well, for the first part, my first interval is -infinity, comma, -2, and then I'm going to put a bracket here. Union, recall from the previous section, if I want to list a set that has a finite number of elements, one way that I could do that is using the curly bracket notation. So I'm trying to create a set that just has a single element in it. And so I'm going to have a curly bracket, the number 1, and then a closed curly bracket. And that is the set containing the single element of x equals 1. And there is our final answer for our solution set. Maybe I'll put S equals, and then that's part D. That concludes example 9. Here's a quick tree that we've kind of broken down into when we've been talking about inequalities. In this section, we've been talking about nonlinear inequalities, and so far we have talked about polynomial inequalities and more specifically quadratic inequalities, although we did see an example of a cubic inequality. Now we're going to start talking about rational inequalities. Example 10 says solve the inequality x plus 4 over x minus 2 is greater than or equal to 0. So really quickly, we haven't talked about what the graph of y equals x plus 4 over x minus 2 would look like. So I've included the graph here, and essentially we want to know when is this graph greater than or equal to 0. And it looks like it's going to be greater than 0 before -4, and maybe everywhere after here. And it turns out that this graph has something called a vertical asymptote, and that is occurring right here when x equals 2. And the reason for that is because notice that I have x minus 2 in the denominator, and if I plugged in x equals +2 into the denominator, we would end up with division by 0, which previously we have learned division by 0 is very bad and we cannot do it. It is undefined. So based off just the graph alone, I would expect that my solution set is going to be s equals -infinity to -4, bracket, union, parentheses, 2 to infinity. And the reason that we are including -4 is because look here, our x-intercept is at -4, 0. But I'm excluding 2 because that would lead us to have division by 0. Now, how would we have done all of this if I didn't know that this is what the graph of this equation would look like? So what we want to do is we want to solve for the critical values. And when we're talking about something that's rational, we find the critical values by setting both the numerator equal to 0 and the denominator equal to 0. So let's start off by setting the numerator equal to 0. If I solve for x, I end up getting x equals -4. And if I set the denominator equal to 0, I get x equals +2. So here our critical values are x equals -4 and x equals 2. Now what I want to do is I want to make a number line. Here is -4 and here is +2. Once again, the critical values are breaking up our x-axis or our number line into subintervals. And so my first subinterval is going to be from -∞ to -4. My next subinterval will be from -4 to +2. And then my last subinterval will be from 2 to infinity. And now what I want to do is I want to choose test numbers. And I need something on this first subinterval. I'm going to choose x equals -5. And this next subinterval, I'm going to choose x equals 0. As a tip, x equals 0 is a great test number to choose if you're able to use x equals 0 and it's not one of the critical values. And lastly, on this interval from 2 to infinity, I'm going to use the test number x equals 3. Okay, so I've cleaned up my screen a little bit, and let's go ahead and plug in our test numbers into the expression x plus 4 over x minus 2. I'm first testing x equals -5, and I'm going to have -5 plus 4 over -5 minus 2. That's going to end up equaling -1 over -7, and that's equal to 1/7, which is a positive number. This is greater than 0. So on this subinterval, I'm just going to put a plus sign to indicate that it's positive. And we actually kind of already knew that since we have the graph here, right? So we know from the graph that before -4, our graph is positive or above the x-axis. But still, let's show the algebra behind this. I'm going to choose my next test number of x equals 0. If I plug that into my rational expression, I have 0 plus 4 over 0 minus 2. That's going to end up being -2, which is less than 0. So I'm going to come back to my number line and indicate that that's going to be negative. And then x equals 3 was my last test number. And I'd have 3 plus 4 over 3 minus 2. That's going to end up equaling 7, which is positive. And so on my number line, I can indicate that that's positive. And again, we already knew that. So I'm looking for positive. That's everywhere between or before -4 and after +2, which is going to, again, give us this answer that we've gotten previously. And then we have to check the endpoints. -4 would give us 0, so -4 is included in our solution set, and 2 would be excluded because we cannot plug in 2, or else the denominator would end up equaling 0. In example 11, we would like to solve the inequality -2x plus 1 all over 3x plus 6 is greater than 1. Now, a lot of times students are inclined to try to solve this inequality by multiplying both sides by the denominator of 3x plus 6. If we do that, then we're going to get -2x plus 1 is greater than 1 times 3x plus 6 is 3x plus 6. And if I were to solve this, this is now just a basic linear inequality. I would add 2x to both sides. That would give me 5x, and then I would subtract 6 from both sides. So here I would get 5x, and on the left side I would get -5. I'm going to swap these, so 5x is less than -5, and then if we divided both sides by 5, we'd get x is less than -1. Now, this is not the correct way of going about solving this question, and I will show this in just a moment. So graphed in the blue here, I have shown the graph of y equals -2x plus 1 over 3x plus 6. And I would like to know when that is greater than 1. And if I find 1 on the y-axis, that is this line right here. And so essentially we're looking at the graph and we're wanting to know, when is this above the line y equals 1, or in other words, above the pink line. And notice that that does happen when x is less than -1, but after a certain point, then it stops being. So notice here, this is now below the pink line, so that should not be included in our solution set. So to reiterate, you do not solve this inequality by multiplying both sides by 3x plus 6. That will end up giving you the wrong answer. So how do we solve this? What I want to do is I want to subtract both sides of my original inequality by 1. If I do that, we'll get negative 2x plus 1 over 3x plus 6 minus 1 is greater than 0. Now, from here, we're going to be able to turn this into a form that looks like the previous example, where I have a single rational expression on one side and 0 on the other side of my inequality. And the way that I'm going to do that is I'm going to multiply this by the common denominator of 3x plus 6 over 3x plus 6. And then we have that that's greater than 0. If I do that, I get negative 2x plus 1. And what I need to do is I need to distribute this minus 1 into both of these terms. So I'm going to get minus 3x minus 6. And then we'll have a common denominator, so I can combine this all into a single fraction with the denominator of 3x plus 6. And we want this to be greater than 0. Let's go ahead and simplify our numerator now. I'm going to have minus 5x minus 5 over 3x plus 6 is greater than 0. Now that I have this in the form that kind of looks like what we had in the previous example, we would follow the same steps that we did in the previous example. I have a numerator and I have a denominator. I'm going to find my critical values by setting my numerator and my denominator equal to 0. So we get a critical value or a critical number, x equals -1. Now I'm going to set my denominator equal to 0. And so we end up with the critical values of -2 and -1. Now I'm going to make a number line. I have -2 here, and I have -1 here. So my x-axis or my number line is getting broken into these subintervals from -infinity to -2, between -2 and -1, and from -1 to infinity. Let's choose some test numbers or test values. I'm going to choose x equals -3 for my first one. And be careful, I want to plug in -3 into this expression here because I want to see when it will be positive. So if I plugged in -3, I would have -5 times -3 minus 5 over 3 times -3 plus 6. And -5 times -3 is 15. 15 minus 5 is 10. And then we'll have -9 plus 6 is -3. So that's going to end up being negative. So my first interval, I'm going to put a negative sign there. I'm going to choose my next test number to be -1.5 because unfortunately there are no integers between -2 and -1. And if I replace that in x in the yellow highlighted rational expression, it's going to end up giving me a positive number. So I'll put positive here. And then if I plug in 0, I would get -5 over +6. That is a negative number, so I'll put negative here. Now, because I am looking for when this thing is greater than 0, that's happening based off our number line between -2 and -1. So finally, our solution set S is equal to -2 to -1, excluding our endpoints. And here is our answer. Example 12 wants us to solve the inequality x plus 7 over x squared minus 12x plus 32 is less than or equal to 0. Let's go ahead and factor our denominator. This is going to factor into x minus 4 times x minus 8, and we want to know when this is less than or equal to 0. Let's go ahead and solve for our critical values. I'm going to set my numerator equal to 0. If we do that, we get x equals -7. If I set my denominator equal to 0, and now I use the zero product principle, so I'm going to get x minus 4 equals 0 and x minus 8 equals 0. Then that leads to x equals 4 and x equals 8. Let's go ahead and make a number line now. So here's -7, here's 4, and here is 8. So we're going to need a lot of test numbers. Here are the test numbers that I've chosen: x equals -8, x equals 0, x equals 5, and x equals 9. And I'm going to plug these into this factored form here. So I have x minus 7 over x minus 4 times x minus 8. So in my numerator, I would have -8 minus 7 over -8 minus 4 times -8 minus 8. And something to remember is, really, ultimately, we don't care about what the numerical value is. We really only care what the sign of our final answer is here. So my numerator is going to end up simplifying to a negative number, and we're going to have a negative times a negative in the denominator. That's going to give us a positive. And finally, if we have a negative number divided by a positive number, this is going to be negative. So if I break up these intervals from from -infinity to -7, that's going to be a negative value. Go ahead and plug in the other test numbers on your own and see what values you get. For the sake of time, I'm just going to tell you that the remaining ones, so between 4 and 8, that is going to be negative, and then between -7 and +4, and then 8 to infinity, those are going to be positive. So our solution set is going to be -infinity to -7, union 4 to 8. Now for each of these, I need to figure out whether we're going to put brackets or parentheses on our endpoints. -infinity and +infinity and interval notation are always going to have parentheses around them. Let's think about -7. I have my highlighted expression here. If I plugged in -7 for x, -7 would go right here, and right here. Because, oops, I am missing a plus sign. That should be x plus 7. Now, because my numerator is x plus 7, if I plugged in -7, that would make the numerator 0. And it doesn't matter what the denominator is, as long as it's not 0, which it's not if I plug in -7. So I'd have 0 divided by some non-zero number, which would mean that our overall fraction will be 0, and 0 is less than 0 is less than or equal to 0, so it's part of our solution set. Now with 4 and 8, those are both going to make my denominator 0, which would make it undefined. So I do not want to include 4 or 8 in my solution set. So here is our final answer for example 12. Example 13 says, a large technology company in the Pacific Northwest finds that their profits in millions of dollars can be modeled by the function P of t is equal to t times t minus 8 times t minus 10, where t is greater than or equal to 0 and less than or equal to 24. And that represents the number of months since the start of the company. For what value or values of t does the company make a profit? In other words, when is P of t positive? We will explore the topic of functions more in a later section. So I have this thing we're calling P of t. P of t is equal to t times t minus 8 times t minus 10. And I'm just going to go ahead and erase this part here. we have this expression, and it's a cubic since we're multiplying 3 linear factors together, and we want to know when is this thing greater than 0. We've done this multiple times now, and what's nice is this is already in factored form, so if I found the critical values, they would be t equals 0, t equals 8, and t equals 10, and I can make my number line here. I'm going to start at 0, 8, and 10, and what's nice is because this is an application question, I don't really need to plug in a test number before 0 because I don't really want to know about the profits before t equals 0 because that would be before the company started, and so it wouldn't have existed and there would be no profits, so we don't have to worry about that. We're only concerned with when our input variable t is between 0 and 24. So I'm breaking it up between 0 and 8, 8 and 10, and then 10 to 24. Let's say 24 is over here, and I want to plug in test values there. Let's plug in 1. If I plugged in 1, I would have 1 times 1 minus 8 times 1 minus 10, and 1 is positive, 1 minus 8 would be negative, and then 1 minus 10 would be negative. So if I multiply all of those together, this one is going to be positive. Let's go ahead and plug in 9 now as a test number. I would have 9 times 9 minus 8 times 9 minus 10. This is a positive times a negative, so that is going to leave us with negative here. And then lastly, let's choose 11 as a test number. So I'd have 11 times 11 minus 8 times 11 minus 10. This is going to be positive, positive, and the last number is going to be positive. So multiplying all of those together, we would have positive. So finally, our solution set is going to equal, our endpoints would be 0 to 8, and then union 10 to, and then we'd stop at 24. Now we have to decide, are these going to be bracketed or parenthesed? And 0, 8, and 10 would all make our cubic expression 0, but we want to know when is it going to be greater than 0, not greater than or equal to. And then 24, if I plug that in, that would be a positive number, so 24 would be included in our solution set, and here's our final answer. However, now we are dealing with a word problem, and so it's important to write our final answer in a sentence to describe what our final answer represents. So we can say the company would be profitable between months 0 and 8 and between months 10 and 24. And that's our final answer.